Hello again. In previous tutorials, I have shown how you describe transparent substrates like glass plates by optical modeling, and I have handled the analysis of oxide layers, oxide and nitride layers, and also I have given an example about using the batch control feature of code, Scout and Code, to analyze many spectra in an automized way. This tutorial now combines all of these things, and I will show you how you can use code to get thickness profiles if you're working in a factory with a large area coater producing coatings on glass. In machines like this, you often have the problem that you have to check every cathode group that produces one of the functional layers before you do the real production in a kind of tuning phase. So you have to find out if the profile is even enough and if you produce the right optical constants and the right thickness values that was proposed for the design of the coating. So here, what I show you here is a model that works already for a titanium dioxide layer on float glass. So the layer thickness is pretty high, about 53 nanometers, which is important in order to get safe optical constants because we need to have a maximum here in the reflectance and a minimum in the transmittance, but the maximum here in reflectance, that's the most important feature that gives us some safety concerning the optical constants, the refractive index value of the material. So the fit already works. So if I tune the thickness here and press start, that's what we have covered before, how we can make these models. And we are now in the position to apply this model to thickness profiling. That means we want to do the analysis for measurements that have done on many different positions on the glass. The ideal feature of code to do this is the batch control window. So if you press F7, you will find the batch control window here, and if you say prepare new batch fit, code will prepare, as I have explained in the other tutorial, a results page, a page of input options, and the prefit page. But here the most important part is the results page, where we want to collect results for all the positions on the glass. Well, getting the measured spectra can be tedious if you do it manually. Code offers a few mechanisms to do that in an automized way, and one is to use the command prepare new results page, and you can see here that there are several options for files that contain all spectra of all positions, like the Optiplex ngCube file generated by the Zeiss Optiplex software, or if you have a coater produced by Van Arden, they produce ex-situ files which contain all the measurements done by the traverse system. I have received data that I can use for this tutorial by one of my customers in an Optiplex 5.1 format. So I will select this one, and in this format you have to specify the pane ID. That was 777, and then you have to specify the folder where the data are, and the data are in this folder, and then code will prepare basically data columns for all the input spectra. It will read the position information from the Optiplex file and enter the positions in millimeters here in this column, and all the file names that we need for every distinct position on the glass. So we can just try if the fit works. So we can put our cursor here in column 5 and click on fit current sample, and then see if the fit really works. It does, and we can hope that the fit will work for all the other positions as well. So if we go back, here are the results for column 5. So that's for the beginning. Assume that the stoichiometry of the material is the same everywhere, so that the optical constants are not changing. We will see if that's a good approximation, but let's do that first, assuming everything is constant except the deposition rate, which is position dependent. So we have to go to the list of fit parameters. We can do that by pressing F7 and right-click the list fit parameters here, or there's a shortcut. We can hold the Control key down and click on this view element that shows the fit parameters, and that will open also the list of fit parameters. Here we have 5 parameters, the first 5 that modify the optical constants of the titanium dioxide. The parameter number 6 is just the layer thickness. So if we freeze all the parameters except the layer thickness, then we will just have a thickness fit, assuming that the optical constants are not changing from position to position. We can do that using one of the actions commands here, and use the command action set all to frozen, and then we go back to the last one and press F5 as often as it is necessary to go to the downhill simplex setting here. Well, it's a very good approximation. I hope so, at least, that the thickness will be more or less the same everywhere, so the variations are small. So we can easily use the downhill simplex method here and don't have to use a grid fit, which makes the fit pretty fast. So let's now start the batch fit. There's an actions command that we can use here. Actions start batch fit, and now we will go from position 1 through all the positions. Actually, the fit has not started, so let's go to batch control and press go here. Let's hope that this works. Okay. So now we go pretty fast through all the positions. Since we are fitting only the thickness, this is easy. And we can wait until position 31 is reached, which is the last one, and then we can go back to the list of to the batch control window and take a look. All the parameters here concerning the optical constants are identical from column to column. Only the thickness varies, and as I have shown in the tutorial about the batch control with a silver layer on glass, we can visualize rows in the batch control window, and that's what I will repeat now, because I want to see the thickness versus position. Position here in millimeters is in row number 3, and we go from cell B3 here to cell AF3, and the thickness, maybe we can remember that later on, the thickness is in row 22. So we now go to the list of view elements, generate an object called batch control graph rows, and let's call this thickness profile, and let's do all the settings. We have to go from, well, the x values, the position values were started in cell B3, and the last one was in AF3. The thickness values were stored in B22 to AF22, and now we can give the graph a title: thickness versus position. Line mode should be 16 little circles. The grid line mode should be 1. We can have a frame mode 3 that gives us grids, grid lines with painted in gray actually. Okay, the thickness, the position range is, I think it's a pane with a width of 3,200 millimeters. We can have ticks every 500 millimeters, and this should be called position on glass in millimeters. And here we have the thickness in nanometers. And let's assume, I think the values that we got were between 45 and 55. We can I can refine that a little bit later. So that should be it. Let's see if we can see the profile. Okay, that's the thickness profiles. Actually, we can have it drawn from 50 to 55. Let's see if that should work out. Yes. So I press Control, click on this graph, and change the minimum for the y-axis to this value. And here we see the thickness profile that we have obtained in the batch fit. Actually, I'm going to generate more of these graphs on the right side. So I will move this to the side, make this graph here much smaller so that it can fit on the left side. Move this to the right, and this here. Sorry for this rearranging. Okay, but we need more space for more results. So this is thickness versus position, and in the next step I would like to show you changes, or I would like to show you what we get if we assume that the refractive index values or the optical constants of the titanium oxide are not constant. So we unfreeze all these parameters and do the fit again to get a more precise model. Anyway, the fits are all good. Actually, I showed you already in the last tutorial about batch control that we can visualize all the results by using the command actions loop through results. So this loads all the measured spectra and the fit results here, and we can just verify that the fits were all pretty good. So probably there is no real reason to assume that the optical constants are not the same. So the fits all nicely match the measured data. But anyway, to be complete and prepared for the case where we have a variation of the optical constants with position, we should open up this possibility. I keep the control key pressed down, click on this, and go in the list of fit parameters to the actions submenu, set all to downhill simplex, and now we can rerun the batch control um, with all parameters. Sorry, I should update this, with all parameters set to downhill simplex. So we can now go to the batch control and say go again. And we will now see also a variation of the first 5 fit parameters. So the fits now take a little bit longer, and anyway, they cannot be worse as they were before. Even they might be a little bit better. And later on, we will take a look at the results for the optical constants. And there I will show you how to use what's called optical functions in code to extract information from an optical model that has been obtained in a fit. So actually what we do here now is we produce new fit results for position 8 now. Next one would be position 9. So if here we still see the results that we have obtained, basically the batch control cells. And if the thicknesses would be really different now in the second attempt to fit the measured data, we could see jumps here. There was a little jump here. So the thicknesses change only a little bit, I guess. The overall profile will be the same, which means that the optical constants of the titanium dioxide are not really position dependent too much. But we will generate a graph later on. Okay, I left out a few fits in the video. They were all nice. Here is the last one, and we can now take the next step in order to visualize results in a convenient way. Actually, in order to find out how the stoichiometry of the titanium dioxide changes from position to position, well, the tedious way would be to reload the fit parameters, to recompute the model, and take a look at the graph of the optical constants. That would be very tedious to do that for 31 positions on the glass. There's a simpler way, and I would like to show you the option to use so-called optical functions that are available in Scout and Code to extract information once the optical model has been computed. So let's take a look at this list, which is called optical functions, which is here. And actually, it's a very simple list. You can have values, you can have a function, which are called optical functions, and just specify the decimals that you want to use to display the number. The functions have all the same structure. You have to give the name of an object, and then you have to specify what kind of quantity you want to see. Luckily, there are templates here that we can use, and there are templates for materials, layer stacks, and spectra. Let's use a template for materials. We can extract all kinds of quantities, and in our case it would be useful in order to check the stoichiometry of the titanium dioxide to extract the refractive index, the real part n, at a certain wavelength. So we can use this template here, and we have to fill in the material name. We have to type that correctly. This is compared with the list of materials here, and if this material is called TiOx, we have to use the same name here also. Let's display the value with 4 digits, and then we get the value 2.8014. We can also display other quantities. For example, we can generate a new object, copy this, and we can basically go to the near infrared and display the optical constants there as well. Lower, that's the material with a strong dispersion, so we have a difference of 0.4 roughly between this wavelength and this wavelength, or the refractive index at these wavelengths. And just to show you what you can do for layer stacks, you can compute specific values, reflectance, transmittance, absorption, or the sheet resistance, which is not so important at the moment. And for spectra, you can compute a lot of sometimes interesting values. You can pick simulated values, measured values at certain wavelengths or frequencies. You can compute average values in wavelength ranges, or you can do an integration of a spectrum and extract this as a number. And you can also do a Fourier transform of the spectrum if you have, for example, periodic patterns due to layer thickness interference of thick layers. That's a shortcut in order to get thickness values for very thick layers, actually. So here we are just interested in the titanium dioxide, so we can leave it like that here. And now, well, of course, you can display these values in a view. You can only, well, what you have to do in this case, you take the optical function, you drag and drop it to the view element list, and then you give it a name, titanium TiOx, N at 400 nanometers, and then you can see this value here, and with a little bit of extra work, the distance between the output and the text, the output number should be a little bit smaller. So you could display this value here, and once we go through the batch control results again with the command actions loop through results, you can see how the refractive index values here changes. Actually, not very much. Okay, let's stop this. But there's an even nicer way how to do this. Go to we have the defined new optical functions, 2 of them in the list of optical functions, and if we go to the batch control window, we can now generate these values here, and we don't have to do the batch fitting again. We can just do the following. We use the command actions, recompute functions, which does the following. For every column, for every position on the glass in this case, the fit results are loaded into the model. The model is recomputed with the results of the batch fit for this column. And then the optical functions are computed and then entered into this table as well. And this is done for every row, for every column, so for every position. And so without doing the fits all again, we just enter the new functions in addition to the existing values to the table. So if I click that, you can see that this is pretty fast. So we get values here for the refractive index versus position, and of course we can also generate a graph doing this. So this is row number 26. So we can go to the list of view elements and duplicate the thickness profile that we have defined before and call this now refractive index profile. We don't have to change too much. The 22, row 22 goes to row 26, and in the graph we should call this titanium dioxide N, let's say N at 400 nanometers versus position. And here we have, let's call this refractive index versus position. And here we are more specific. N at 400 nanometers. And as far as I remember, the values were between 2.75 and 2.85. Small differences only. So now we should have a second graph here, and we can move this to the side, and the second graph below, thickness versus position, and this is refractive index versus position. And in my point of view, this is a very small variation of the refractive index, so it's not really varying too much. Okay, let's check. Let's put this here. Actually, I have to change this distance of value and text to a smaller value to make it fit nicer. Okay, so this would be a method. It would almost be a method that let's say the operators in your factory could use. And in order to make it real simple for them, I have generated commands here. Actually, these are so-called scripts, and they execute certain commands, and I will make another tutorial about scripts. I just show you here the content of this one. Scripts have a text that show what the script will do, get new profile, and then you can execute some commands. In particular here, these commands tell code that the user should select a new pane ID from an Optiplex CSV file and then start the batch fit. So basically that's the content of these scripts here, and we can now check if this works. For the next pane, get new profile. Next pane ID would be 778, and then we have to select the folder. Actually, this will not have to be done in the next step, but for the first time now the folder has to be selected. Now code loads all the spectra and then starts the batch fit for the next pane ID, and then enters the results here. And I don't know if you can remember the last profile. We can rerun that later on. The thickness is certainly very different. I hope that my scale here will work out. And since the fit is now running for quite a while, I will be silent and I will just skip the fitting while the video is recorded, and I will cut out this part and come back to you in a while. Okay, here I'm back. We are in the final round of the fitting. Actually, some of the thickness values are larger than the 55 nanometer limit here, so I have to increase that. Instead of having a maximum of 55, it should be good to have it at 58. That gives a nicer profile here. And the refractive index versus position, luckily, is in the same range that we have set before. And again, the variation is very small. Okay, so this is a method that will be very useful for operators in the tuning phase of a large area coater. And if you prepare configurations like this for every cathode group or for every material that you produce, for every layer with reasonable settings, maybe the operators will be thankful that you show them these profiles and help them to make the profiles as even as possible and to see what changes in the machine settings lead to concerning the thickness homogeneity and the homogeneity of the stoichiometry. Of course, the brain production control software does this even more automatic, so you get profiles and profile graphs from pane to pane, even more elegant as it is possible here. But these solutions using code alone can also be quite useful. Thanks a lot. This is the end of this tutorial. Bye-bye.